Welcome back to the lectures in quantum chemistry, introductory and also molecular spectroscopy. This lecture continues the review of elementary mathematical functions and their properties, as I have started in the previous lecture with some description of exponential and Gaussian functions. Now, today we shall look at some of the other functions that we need for the purpose of this course, and we will start with one of the most elementary functions, trigonometric. Namely, let us start with f1 of x is a constant a1 times sine another constant a1 of x. This is periodic, and the period is between 0 and a1 x is equal to 2 pi, or x is equal to 2 pi by a1. Okay. That is the value. So, this function repeats after that value of x, and all of us know that this function can be plotted in a very simple manner. If this is f1 of x and this is x, then what we have is the function starts with 0 and reaches again 0 at half the interval, and you know the sine function goes until it reaches 0 again. So, this, if you call it as 0, this is the maximum that you have, and this maximum is, if you recall the function as a1 sine a1 of x, a1 sine a1 of x, the maximum is a1, and it happens for the value x is equal to pi by 2 a1. So, that this becomes sine pi by 2. Okay. The 0 happens for x is equal to pi by a1, and the minimum, so if you draw this axis, the minimum is minus a1, and this happens for the value 3 pi by 2 a1, and this one is the last one, namely 2 pi by a1. Okay. So, this is the simple oscillatory function, and the function is important in quantum mechanics in that it satisfies the differential equation d square f by dx square plus a1 square f is equal to 0. It is a very elementary differential, second order differential equation. a1 square of f is equal to 0. Okay. That is easy to derive, because you know df by dx is a little a1 cos a1 of x, and the second derivative d square f by dx square is the derivative of cos is minus sine, and therefore, you have a minus a1 square, and this is a1 sine a1 x, therefore, that is a1, which is that equation. Okay. And cosine a1 x, if we have to write that, is different from the sine only by a phase factor of pi by 2. It is an independent function, trigonometric function, but the relation between cosine and sine is that it is a1 sine a1 x plus pi by 2. Okay. It is just an argument of pi by 2 that differentiates between cosine and sine. what is the integral of sine a1 x? Okay. The integral, if you leave it with the constant a1 outside, simply gives you minus a1 by a1 cosine a1 of x, and if you do not have the limits of integration, you normally have a constant which is undetermined, and the constant is determined if you do the integration between specific limits. And the limits that we often will use is a function something like 0 to 2 pi by a1 sine a1 of x squared a1 of x dx. This is one function we will see, and another function that we will normally use in this whole course is a product of two of these functions, 2 pi by a1 sine n1 a1 of x sine n2 of a1 of x dx, where n1 and n2 are integers, and here of course we may as well do the integral sine square n1 a1 of x dx between 0 and 2 pi by a1, sorry, this is a1 square and this is a1 square. So, different types of these integrals and functions will be used in the course, and it is very easy to see that the integral of the function itself 2 pi by a1 sine a1 of x dx, the integral itself is 0, that you can verify from the figure here. See that the integral is the, if this is the function, the integral is the area of this function, and you can see that the area under the first half of the interval 0 to pi by a1 is positive, and the integral in the second half of the area is negative. Therefore, a full cycle the integral is 0. On the other hand, the square of the functions are not like that. So, if you plot the square of the function, for example, f1 of x square, if you do that, that is a1 square sine squared a1 of x, and you know that the sine square function does not have any negative component, and also it has a slowly increasing in the beginning and reaching to a maximum value and reaches 0 again, and then it continues that again. So, this is a1 square, okay. This value, this is f1 of x square, this function is plotted on this axis and this is the x axis, and you know that this is the 0 that you had earlier, namely pi by a1, and this is 2 pi by a1. The sine square integral, if you have to do that, a1 square sine square integral a1 of x dx is again between 0 and 2 pi by a1. This integral is not 0 because both the components of the area are positive, and therefore, it is easy to do this integral by simply using the formula that a1 square by 2 between 0 and 2 pi by a1, 1 plus cos 2 a1 of x, sorry 1 minus 1 by 2. 1 minus 1 by 2 dx, and this you can see immediately that the cosine integral, the integral 0 to 2 pi by a1 cosine 2 a1 of x is also 2 complete cycles of the cosine functions, and that will be 0. So, what is left over is simply a1 square by 2 0 to 2 pi by a1, and you have dx, which will give you x, and therefore, it gives you a1 square by 2 times 2 pi by a1, or it is a1 square pi by a1. Okay. This is the value of the square of the function, and these are important when we talk about wave functions which are normalizable, or how to normalize a wave function, etc. And the normalization will involve psi star psi, as we had discussed in the beginning of one of these lectures, that the wave function times its complex conjugate, and if the wave function here is a real function, the complex conjugate is the same as the function itself. Therefore, psi star psi is equal to psi squared, and the psi square integral will be a finite value, and if we use that to define what are called normalized wave functions for interpretation using probabilities. Okay. So, this is about the sine function. Now, another function which is actually not very much used by us, but which is something that you can see in quantum mechanics is going to cause a lot of trouble, is a tan x. Let me get rid of the a1, we will not worry about that. Let us put a1 is equal to 1, and so let this be another function f2 of x, which is sin x by cos x. And you can see immediately that this function is troublesome for us to do any quantum mechanics. As if you plot this function, this is 0, and you know when x is pi by 2, sin x is 1 and cos x is 0. Therefore, if I do x is equal to pi by 2, I have a problem that this function increases, okay, forever. This function increases forever. It goes very steep and it goes to infinity at the value of pi by 2. Okay. So, let me get this pi by 2 here. This is pi by 2. What happens immediately after pi by 2? So, this is between 0 less than x less than pi by 2, this part. Now, what happens after pi by 2? So, let us just change the color, pi by 2 less than x less than pi. What happens? So, you see that sin x is positive, sin pi by 2 is 1, and then from pi by 2 to sin pi, the function decreases. But cos x increases from 0 in the negative direction, because cos x is minus 1 when you go to x is equal to pi. Therefore, cos is negative in the second quadrant, therefore, the whole function is negative, but it is growing from very large negative values. Please remember, cos x is very close to 0 when x is very close to pi by 2. Therefore, this is a very large negative function, and therefore, if I mark pi here, let us see, it grows very large values to from large negative values to 0 at pi, and then up to 3 pi by 2, both sine and cosine are negative pi, x 3 pi by 2. You can see that the function, both of this are negative, and sin x goes to minus 1, cos x goes again to 0, and therefore, this function continues to increase because its the ratio is positive, and this is 3 pi by 2. So, this one is pi, this one is 3 pi by 2. And what happens on this side? Quite obviously, function goes like that. Okay? They are all exactly the same curve in the interval, in the half intervals. Okay? The problem is this function goes to infinity and minus infinity very quickly, and the number of such infinities that this has in a very large segment, it increases. Therefore, such functions are not very useful, but you have to be very careful dealing with functions like these. It is important to have a visual picture or a representation of the simple one-dimensional and two-dimensional functions before or as you go along the course, because they help you in understanding what are areas, what are volumes, and things like that. Okay? So, this is for the sine part of it. Let us go to the next one. We have already done the exponential kx and the exponential minus kx and exponential x square. So, let us start with the complex variable, which all of you know is defined as x plus iy, I is square root of minus 1, I squared is minus 1, I into minus I is 1, minus I whole square is also minus 1. Okay? Those are the properties. And you also know that this is usually written as r e to the I theta, and r therefore is square root of x square plus y square, and theta is tan inverse y by x. And that comes from the representation that x is equal to cos theta and y is equal to sin theta. And therefore, you can see that square root of x square plus y square, it should be r cos theta, r cos theta. Okay? Therefore, the square root of x square plus y square will be equal to r, and the tan inverse comes from that. Okay? This is the exponential function, and we need such functions when we study particle in the ring and also on the hydrogen atom, the angular functions of the hydrogen atom and so on. The complex conjugate of z is x minus iy, and in the polar representation it is r e to the minus I theta. Okay. Therefore, z star is x plus iy into x minus iy, which gives you x square plus y square, and that is exactly what you will get from r e to the I theta times r e to the minus I theta, giving you r square. Okay. That is what the definition was earlier. Okay. So, this is the elementary level. What about the integral of exponential I n theta 0 to 2 pi, where n is an integer? Okay. Okay. Now, d theta, of course. You must remember the Euler formula, namely exponential I theta is cos theta plus I sin theta. You have already used that in this part, okay, or cos theta plus r sin theta. So, when the r is there, exponential I theta is of course cos theta plus I sin theta. What about e to the 2 I theta? This is e to the I theta whole square, and exactly the same thing, cos theta plus I sin theta whole square, which gives you cos square theta. I squared is minus 1 minus sin square theta, so that is the real part, plus I into cos theta sin theta plus sin theta cos theta. So, you have 2 sin theta cos theta, and that you know is the double angle formula. It is cos 2 theta, and this is sin 2 theta. Okay. So, that is also very easy to see, because that is nothing other than e to the 2 I theta. Okay. Therefore, what is the integral of e to the I n theta d theta between the limits 0 to 2 pi? It is quite obviously 0, because you can see that it is the integral of cos n theta, where n is an integer, d theta, plus I 0 to 2 pi sin n theta d theta. Okay. Each one is a complete cycle n times within the interval 0 to 2 pi. Therefore, the areas cancel each other 0 0. Okay. Therefore, this integral is 0. What about the integral psi? Suppose you call the psi theta as e to the I n theta. What is psi star psi? You know that it is nothing other than e to the I n theta times e to the minus I n theta, and that is 1. Okay. Therefore, what is the integral psi star psi d theta between 0 and 2 pi? That you know is nothing other than 0 to 2 pi 1 d theta, therefore, it gives you 2 pi. So, these things are important. And one last one with respect to our course requirement is the integral e to the I n theta e to the minus I m theta d theta, where n, m are integers and n is not equal to m. So, it is between 0 and 2 pi. You can see right away that this is nothing other than another integer e to the I n minus m theta d theta, whatever number that is. Since n and m are both integers, the difference is also an integer, plus or minus does not matter. Therefore, this is also 0. Therefore, we say psi n theta, which is e to the I n theta, and we say psi m theta if it is another function which is e to the I m theta, then these two functions are orthogonal. Psi n and psi m are orthogonal to each other, and we will use this idea later. Okay. Integral generally of e to the I n theta d theta, if you do not have the limits, it is 1 by I n e to the I n theta plus a constant. Okay. So, you can manipulate and multiply these, and you remember e to the I theta itself is given by the Argand diagram from 0 it's an approximate circle. Let us see if I can make it slightly better. Yeah, perhaps this is slightly better. Okay. Theta is 0, pi by 2 plus pi, pi by 2 pi, 3 pi by 2, and this is coinciding also with the 2 pi. Therefore, e to the I n theta has the same value between the ranges theta 0 and 2 pi, and whatever this is faithfully reproduced 0 between less than or equal to 2 pi less than or equal to theta less than or equal to 4 pi, and so on. Therefore, it has for different values of theta, the function has the same value in the domain 0 to 2 pi, 2 pi to 4 pi, 4 pi to 6 pi, and so on. So, keep that in mind. So, one last function that we have to worry about, or two, is that exponential minus kx, x between 0 and infinity. Okay. Actually, you can include both. The integral, all of you know, 0 to infinity exponential of minus kx dx is 1 by k. Okay. Now, what is the exponential when you have a power of x n of x multiplying e to the minus kx dx, 0 to infinity? I think I have mentioned this in the last lecture, and one can calculate this by an iterative, very simple process with the n equal to 1 and n equal to 2, and then generally for any value of n. Okay. And you know that it has to be n factorial by k to the n plus 1. Okay. Yeah, it has to be k to the n plus 1. Okay. What about this integral, exponential minus a x square dx between minus infinity to plus infinity? All of us know that the answer given is root pi by a, but there is nothing here which tells you how to get the root pi. You can see that this integral contains n and k, and the solutions contain n and k. There is no pi here, and how do you get pi? There is a very beautiful story of this function by a very famous physicist called Wigner on the unreasonable effectiveness of mathematics in physical sciences, where he tells a funny story about the integral. But let us not worry about that, let us worry about how to get the answer. So, if we write the integral I from minus infinity to plus infinity e to the minus ax square dx, then you can write I squared is two such integrals, minus infinity to plus infinity e to the minus ax square dx, and a different variable minus infinity to plus infinity e to the minus ay square dy, because both x and y are dummy variables, they are variables inside, and the integrals are independent. Therefore, we can write this as a double integral between minus infinity to plus infinity e to the minus a x square plus y square dx dy. Okay. Now, what does this do? The integration is done over the x and y for all values from 0 minus infinity to plus infinity. So, let us assume that x is something like this. Then for all values all the way from minus infinity to plus infinity, and for a given value of y, y is equal to some value y1. Now, again you do this integration for another value of y, and therefore, you do the double integration, so that you cover the entire xy plane, Okay. Therefore, this integral is a double integral covering the whole plane, infinite to infinite to extent. How do you do this integral? You can also do the same by defining a new variable x is equal to some r cos theta. I think we used the capital R earlier, so we will use the same thing. X is equal to r cos theta and y is equal to r sin theta. Okay. And then we can see that the integrand dx dy in terms of the variable dr and d theta can be seen this way. R is basically the radial part. So, if you have to plot this as a sort of a simple way, x and y, the dx dy is equivalent to doing integration for different values of r, but for all values of 0 to 2 pi. Theta is equal to 0 to 2 pi for all values of r going from 0 to infinity. Okay. Then you have everything, okay. All of them. Okay. Therefore, the integration using polar coordinates is equivalent to the integration using Cartesian coordinates. So, dx dy is replaced by dr d theta, except that there is a small element here called the Jacobian, which tells you how to weight these small elements carefully. Here the weighting is uniform for each of these variables, and that is given by the simple partial derivative dou x by dou r, dou x by dou theta, dou y by dou r, dou y by dou theta. That is the equivalence, and in the lecture notes I have shown you that this is nothing but r dr d theta. Okay. And the limits minus infinity to plus infinity, minus infinity to plus infinity for dx and dy are now replaced by the limits 0 to infinity for r dr and 0 to 2 pi for d theta. Therefore, what is I square now? I square is this integral minus infinity to plus infinity dx minus infinity to plus infinity dy e to the minus a x square plus y square, and that now becomes, because of x square plus y square giving you r square, the integral becomes r 0 to infinity dr e to the minus a r square, and then 0 to 2 pi d theta. There is no theta dependence here, therefore, this gives you 2 pi. This is the origin of the pi that comes into the I square is proportional to 2 pi, and this integral, if you calculate, you will get the answer 1 by 2a. Okay. Therefore, the integral I square is 2 pi by 2a, and that is pi by a. Therefore, what is the integral I? It is root pi by a. Okay. This is extremely important, and any further integration x raised x square from minus infinity to plus infinity to the minus a x square dx, or x raised to 2n e to the minus a x square dx from minus infinity to plus infinity. Any of these integrals can be done from the elementary integral through a sequence of steps, and there are general formulas for this. It is important that I have 2n, n is an integer, and if it is an odd integer x raised to 2n plus 1 for example, then you know that this function e to the minus ax square. If you call this as a function of x, then function of x for the minus value is the negative of this function, and therefore, this is called the odd function. Okay. And odd functions have this beautiful property, namely between symmetric intervals minus a to plus a, f of x, an odd function of x is dx is 0. Minus a to plus a, f of x, an even function of x, f of x is an even function, dx is 2 times 0 to a f of x dx. Okay. So, these integrals involving powers and of polynomials of x multiplied by the Gaussian functions are also important in the study of harmonic oscillator and later in spectroscopy. Therefore, some of these mathematical exercises you may please go through and refresh. Please refresh some elementary integrals. I shall give you in the lecture notes a small collection of formulas that you might need. There is no need to remember any of them. If you need them in the examination or in the assignment, you can look up to it. Examination will contain that, but elementary integrals and differentials, differentiation are important for you in order to follow a course on quantum mechanics and spectroscopy. We shall not continue this any further. We will see the mathematics as and when we need them, and depending on the model problem, we will discuss that at that point. But a preliminary review like this would hopefully help you when you see the same thing again, and at that time when this is being described, you will recall. I hope this is a very elementary, but it's an important exercise for you to remember, and we'll continue with the particle in a box model in the coming lectures, and we'll start solving the model problems. Until then, thank you very much.